I do not see any hands for objection of recorded, so I start the recording now. So once again, welcome to this webinar. Today, we already have had in the past the UK, the Netherlands and Italy present their initiatives. And today we give the stage to the French National Initiative on 6G. Basically, the goal of these webinars is to provide a floor to all the national initiatives to share their achievements and highlights of their key results so far and position themselves strongly in the European research ecosystem. Without taking much time, I would like to open this webinar and I would like to give the floor to Colin Wilcock, who is wearing many hats. He is the chairman of the board of 6GIA, vice chairman of the board of SNS COO, and vice chairman of the board of ETSI. So, Colin, the stage is all yours.
Thank you very much and welcome everyone. It's very, very uncomfortable wearing so many hats on such a hot day, but let me see what I can do. So these events are very important and really the starting place is what we're trying to all achieve. And foremost, what we're trying to achieve is one global 6G standard. And that 6G standard cannot be created or just for one particular country or one particular region. It needs to be a world standard. It needs to be developed by many different organizations across the world, and it needs to meet the requirements of all the users across the world. And this is very challenging. And if we zoom in on Europe, we want to make sure that we have influence on that standard. If we look across all the various ICT domains, computers and compilers and cloud and satellites and telecommunications, we unfortunately see that in many of these areas, Europe is not a strong player. We don't have top 5 companies. If you look at cloud, if you look at AI, if you look at software in general, if you look at the hyperscalers, we unfortunately don't necessarily have particularly strong position. But telecoms is fairly unique. In telecoms, we do have a place at the table. We are one of the leaders. We have 2 of the 3 major vendors based in Europe. And historically, we've been very strong in this space. So it is right today and also in the future that we leverage that strength. Firstly, we need to make sure we retain that strength in research, development, and products in the telecom space. But secondly, we should be trying to build on that success and trying to make Europe successful in related domains by building on top of that strength in telecoms. And that's really what this webinar today is about. It's about showing the strength of 6G research in France, not in isolation, but as a way of helping Europe work together. By having these seminars, what we hope is we're going towards having one understanding of what's going on in Europe. At the moment, we have many different instruments. We have a European level in SNSJU, also in Celtic. We have the national level in many national programs, Holland, Germany, France, Finland. And to get that influence for Europe, we need to work together. We need to have understanding of what are the key technologies that are being developed in Europe. What are the key use cases? How can we work together to have a stronger impact? And hopefully today we will get a better idea of some of the key areas that have been looked at in the French program. And we need to see this as a first step to better integrated working together in the future. So I hope that through the people participating in the meeting today and the many people who will look at this online after we've recorded it, we can start building connections, not just within France, but from France to Europe and from Europe to France. And through that, improve the awareness and the impact of French research. So with that background and with much interest of what is going to be presented today, I hand back to the moderator. Thank you.
Thank you, Colin, and thanks for the kind words and emphasizing on how we can have a global harmonization on the topic. So without taking much time, let's hear from our first presenter of the day by Philip Wisnia. He's a research director at CNRS. He's going to present on the radio frequency test facility network and the state of art for advanced hardware devices. So, Philip, the stage is yours. Please go ahead and share your slides.
Okay, thank you very much.
For audiences, it's important that we have an interactive session, so feel free to drop down your questions in the chat. So once the presentation is over, we are going to look at the questions and we'll get into the discussions. You're
So
good to go, Philip. Your
okay,
slides.
thank you very much for this nice introduction. Good morning, everyone. Yes, this will be the first of 3 presentations, and this will be focused on let's say, hardware stuff. And then my 2 colleagues, Philippe Martins and Raymond Knopp, will insist on other parts of 6G research perspectives regarding platforms, other types of platforms, but infrastructure platforms. All of this started with a French program, which we'll call PEPR. And this program are parts of Investment for the Future program for the national government, which is focused on all research aspects dealing with the future communication infrastructure, future generation mobile communication. And among this research program, there is this base which is about forming a platform, an infrastructure of platforms dealing with all aspects of experiments we can do about future generation of mobile communications. And the first aspect I will deal with is the aspect on the left. So, which is called RFNet, Radio Frequency Test Facility Network. But before focusing on that part, our main objective is to build up a network of platforms at the highest technological level. And these platforms will be or are already open to the community at large to meet various requirements about characterization, experimentation, and to establish proof of concepts serving the research goal of our partners. And these platforms are key in the research programs we have in this PEPR, future generation of networks, which covers many aspects of research, starting with the architecture of networks, dealing with IoTs, dealing with computation based on these networks, but also on security aspects, and also about sustainability of these networks in the future. So this sets of complete research axis which involve many researchers. It's about 300, 400 researchers, and it involves about 100 doctoral studies and 60 postdoctoral studies. So I will describe a little bit about RFNet in the few minutes to come, and then Raymond will describe the Slices Affair initiative, and the NGC IoT will be described by Philippe Martins. So first of all, I will focus on the characterization of components and hardware subsystem. So what is all about? So it's about an academic network which is dedicated to resources for radio frequency characterization. And nowadays we know that with the advent of future communication paradigms, there will be a lot of work to do in that domain, which involves many aspects, such as the increasing frequency range of communication, or the use of different type of devices, the use of MIMOs, the use of beamforming, and all of that will be or are carried out, are dealt with this network. So the mission is to develop, maintain, and provide cutting-edge metrology infrastructure at the national level, and to support any research and development of hardware components for future networks. So the origin of RFNet, it was born from prior reflections, but the opportunity was seized in 2021 with the launch of this PEPR 5G and Future Network program. And in September 2021, the French government appointed CEA, CNRS, and the IMT as coordinators of this program, and we take profit of this program to build up this RFNet initiative, which is a CNRS initiative. So for now, the RFNet is made of a core group. And this core group is consists of 5 laboratories, which are called in France UMR. They are all with CNRS as a stakeholder of these share units between different universities. But you have an idea here of the network itself. Not that it will be expanded probably by 2027 to other CNRS units as well, which will bring up some new infrastructures, some new platforms to complete our platforms nowadays. So what is now the RFNet network? It's about different types of characterization. So now we have over 70 types of characterization with corresponding resources, of course. The value of the equipment, which is shared between all our labs, is about 30 million euros. The occupied area is about 4,000 square meters. And there are all of these resources are, all of these platforms are staffed with over than 20 persons. And also, most of these platforms are open to multiple people who are trained before using these platforms themselves. That is to say, one of the most important thing is if we deal with platforms, it's very important to open them to other people, to collaboration, so that these platforms can be shared with people and we can work all together in research program that involves these platforms. So there are 5 types of characterization covered by RFNet nowadays. So all of these concerns characterization of material properties. It's only about radio frequency characterization of material properties, not chemical or physical properties, but only about using proper materials into the wave signal building of communication. Another part, which is also very important, is the characterization of active and passive components and circuits. It could be any type of circuits. We can think about radio frequency front ends, of course, dealing with power amplifier, low noise amplifiers, passive components whatsoever. Another part is about antenna radiation characterization. That involves many, to be very quick, many anechoic chambers, that encompasses a very broad range of frequency for the test of antennas. The characterization of functional systems consist of different types of characterization dealing with, for example, with EMC, with some physical layer communication test as well as some measurements about energy consumption of different devices. And then another part, which is about propagation channel sounding, which involves, for example, the propagation channel in the frame of a MIMO configuration or in sub-terahertz frequency range as well. So all of this is set in different platforms, as I mentioned before. I will not enter into details, but here you have some slides about the types of characterization of material properties. So it's about permittivity, permeability, saturation of magnetization, hysteresis loop, and it spans frequency range from a few hertz to the terahertz range as well. So about characterization of active and passive components, there are a set of platforms which involve mainly probe stations in very, very different frequency ranges as well. And again, we have a series of platforms which are different according to the type of calibration, the type of probe stations, the frequency range which are addressed in the different labs of RFNet. The same thing with antenna and radiation characterization. We can have near field, far field measurements. Depending on the configuration, the frequency range can span from 100 megahertz to 500 gigahertz. Of course, in that domain, especially if we deal with centimetric or millimetric or submillimetric frequency ranges, the type of environments from one measurement to another are very completely different. So there are in total 9 anechoic chambers to perform different measurements across the RFNet network. Okay, the fourth one is about EMC measurements, telecom measurements, or energy efficiency measurements. Again, there are a range of platforms. Among them, some kind of platform which are quite interesting for mobile communication characterization, which are reverberation chambers. So reverberation chambers are chambers which are used for EMC measurements, of course, but they are also used for characterization of sensitivity or total radiated power, looking at the mask of communication, for example, or checking of the mask, communication mask. So reverb chambers by now are also a research tool for the future. And the last category is about propagation channel. So there is an illustration there on the left of a system which is available in one of our platforms, which is about MIMO propagation sounding, which is quite of a rare equipment for this kind of characterization. If you look at cell-free communication paradigm, for example, this is something which is very, very, very important to get an idea of a propagation channel into this kind of spatially spread set of antennas for communication. Yeah, and to end with this presentation, I will just illustrate what is the future of RFNet in terms of short-term investment projects, because there are some trends which are very important to address now. And in these trends, there are here 5 examples I give in total. First of all, on the left, about antenna measurements. If you go to submillimetric measurements, it is important to make measurements which are rapid enough. I mean, if you look at the spatial distance between each point of the measurement, then due to the wavelengths, the number of measurements is huge, I think. So in that case, it is important to get protocols which save some time for measurements, for this kind of very high frequency measurements. The same applies for channel sounding, for cell-free measurements, as I mentioned before, and for sub-terahertz measurements. Once again, the type of equipment which are available nowadays for channel sounding must be developed. Another important aspect of 6G communications is about intelligent reconfigurable surfaces. These RIS stuff are at the heart of many experimentation to come. And for that, it's very important to develop appropriate protocols and testing resources. It goes from intrinsic characterization of this kind of surfaces, for which the protocol must be entirely invented, probably. And then there are also scenarios which are well defined in some standards, but for which we need also to develop appropriate experimentation. And this is something which is very transversal for all the platforms we are developing, either at RFNet or SLICESFR, or even including the NGC IoT, for example. The fourth part is about active components. It's not the same thing to test active components in standard frequency range. When you come to very high in the millimetric range measurements, you need to adapt again with the different test beds in order to take into account these characterization of high frequency components. And the same apply for the materials themselves. If you look at dielectric permittivity or magnetic permeability of materials, we know that the characterization of these materials in a low frequency bands, let's say, do not expand to the high frequency range. And we need specific measurements in this high frequency range if it goes up to sub-terahertz frequency range as well. So this is an idea, a rough idea of what would be the next investment project, to give us also a color about the fact that these platforms are not only platforms where we deal with tests. We have to invent tests themselves in some parts. So these platforms are also a research tool, and even if it is sometimes used as, let's say, a simple test. But this is also about research, and that's my conclusion for this presentation. And RFNet is obviously open to collaboration. We organize ourselves to make this open to different users in France, but also, of course, outside. And here, this is a picture of a very large anechoic chamber, which is part of our network. It gives you an idea of the type of equipment which is necessary to deal with antenna measurements in the far field. So it's a huge installation there. Of course, the photo doesn't give any dimension, but the length of this chamber is about 30 meters, just to give an idea. So thank you very much for your attention, and I'm open to any questions, of course.
Thank you, Philip, for enlightening us on the resources that you have at your premises in CNRs. And yeah, now the floor is open for questions. I do not see any burning questions in the chat, but if anyone wants to ask anything, please unmute yourself and go ahead. Looks like not, but anyway, questions could be coming in the chat in some time, I think. And you're just on time, Philip. So let's go to the next speaker, who is Raymond Knopp, who is a professor at Eurocom. So Raymond would present us on the French node of SLICE's RI, access to the experimental services in field of network protocols, radio technologies, and distributed computing. So with that, I give the floor to you, Raymond.
Okay, just give me 1 second.
We can see your slides, but not in slide share mode. And now we can see. You're good to go.
Okay, thank you very much. Okay, so I'm going to talk a little bit about the, let's say the post 5G or 6G component of SLICE's RI, and in particular, what's going on in the French node. So I'll just give a brief introduction about research instruments and what SLICE's RI is all about, and then I will dive into the so-called post 5G blueprint, and then give some status and lessons learned. So first of all, why do we need a research instrument? First of all, the research instrument is not a testbed, which is too specific, and it's not necessarily linked to a particular standard like 5G, 6G. It is more generic than that. It has a very broad scope and a very long-term vision, and we'll see what that is in a second. Some of the key aspects about the research instrument, the way we intend it, are reproducibility, output to standardization, definitely scalability and sustainability over time. It should be interdisciplinary and allow for multi-user access. And on top, there has to be a very solid governance, which ensures the necessary procedures to manage the infrastructure, the underlying infrastructure of the research instrument. So that's what we mean in this context. Just to put it in a global context, you know, these are examples of what we would call the third generation mid-scale test platforms, mid-scale in terms of budget. In the United States, you have the platforms for advanced wireless research, which are completed at this point. Some of them are still running, but the program is more or less complete. Other platforms or test infrastructures like the fabric infrastructure for interconnecting different sites, the Coliseum facility in Boston, and bridges. So that's you know, fairly complete image of what's happening in the academic world in the United States. And I'd like to stress that this is really targeting universities in the United States. In Europe, of course, we have Horizon Europe, and the SNS falls into that framework. In particular, the SNS Stream C, which is funding a lot of the let's say platform-oriented research. But that's a nice mix between industry and academia, with a little bit of bias towards the industry side, I would say. Similarly, in Japan, you have other initiatives, and also in China, with comparable amounts of funding globally on all parts of the in all parts of the globe. But I still would call these mid-scale, and really these are all what you could characterize as test platforms. It's a little different than the research instrument that I described at the beginning. And that's where SLICE's RI fits in. It's somewhere in between the mid-scale type infrastructure and large scale. In fact, it's trying to go towards large scale. And it's in the context of the European S3 framework, which is really about research infrastructures. And what's really important is these infrastructures, they have to support a scientific methodology, which might be a little bit different than, say, the SNS. program. And this is a joint investment between the European Union and the member states. And the Slices FR initiative, if you like, is the French contribution to Slices RI. And Slices itself was the first in digital sciences to enter this S3 roadmap. And that happened in 2021. And basically, it is a research instrument to support academic industrial research community that will design and develop and deploy next generation of digital infrastructures. I'm sorry, my son is in the background because he's home today. And this is supposed to be a distributed research infrastructure or research instrument that provides specialized instruments on very challenging research areas of digital infrastructures, which aggregates networking, computing, and storage resources across the different countries. In terms of scientific domains, it targets networking protocols, radio technologies, services, data collection, parallel and distributed computing, and in particular, cloud and edge-based computing architectures and services. Today, there are 26 partners from 16 different countries, 12 of which have political support from the national ministries and are included in 7 national roadmaps. France runs the Slices RI, and it in the process now of putting in place the legal instrument that will coordinate all of the various partners. And you can see the Slices FR at the top. That is the French contribution, but there are 15 others that are. The timeline is, I'll go very quickly, is we are at the beginning of its life, and it should go on till around 2040. So this is a very long-term, and that's why I was saying before, the long-term vision is important and sustainability is important. So what is the basic methodology that we're interested in? First of all, it's centered around community-defined blueprints with experiments at the center. So the blueprint, in a nutshell, is a means to help collaboration between engineers and non-engineers that work together on developing applications. It defines a common terminology that doesn't require in-depth technical knowledge in order to produce a consistent vision on the application with a focus on the future objective. So it is there to pick up the right resources, be iterative, review and validate, and keep as a baseline. Right? So if now we turn to the 5G component, because inside of Slices RI, there are various blueprints, but the 5G is in some sense central and key to today's discussion. It is meant to separate the user plane and control plane functions, modularize the function design. This is what people typically call network slicing, and define a set of interactions between network functions as services. It is meant to enable direct interactions between the network functions and the services and minimize dependencies between access and core networks. Underlying also is the notion of having network functions which are stateless. So basically decouple the compute from the storage and also support some form of exposure capability. Again, in terms of compute or storage. And so basically the 5G blueprint is trying to adhere to the 3GPP 5G system architectures principles. And the actual infrastructure, you have to see it as a collection of central cloud functions, which are distributed in the various sites, and then edge sites where the edge comprises perhaps some edge compute, but most definitely the radio access network components. And today there are various sites that are being built up, and some of them are actually being built up in the context of SNS. There are some Stream C proposals where some of the sites are exposing their services in that context as well. So in the end, what is this all for? And I'll go over very quickly. There are aspects related to vertical service integration and testing. There are aspects related to software-defined networking, radio and network development, or software development, providing low-level access to radio resources, for instance, terahertz type resources, and also the joint use of a post-5G infrastructure and high-performance computing resources. This could be in the framework, for instance, of digital twins, for code generation or for fuzzing. So, but underlying all of this is we want to have three things. Number one, repeatability, where the same team on the same experimental setup can run experiments in a repeatable fashion. Also reproducible in the sense that different teams can use the same experimental setup and generate reproducible results. And also replicable, where different teams can reproduce and replicate on different experimental setups, on different labs. I will skip over the individual for the interest of time now. What's very important is everything is documented and with a reference implementation. So the concepts have to be fully documented, and there is a reference implementation which can be, for instance, using technologies like Terraform, which are common to Amazon Web Services or Google Cloud platforms, or in general OpenStack platforms, and Ansible when it comes to deploying the software. It should rely as much as possible today on Kubernetes-based infrastructure and use technologies like Open Interface and others. The software and hardware, I can give you some details a little bit later. But basically, the complete documentation should also be coupled with training material. And in the context of Slices, training is known as Slices Academy, so that both the platforms and the material can actually afterwards be used in a tutorial or in a classroom context. So these are some of the examples of the tools. You can see there are web-based tools. There are also software repositories like GitLab and other means to document the blueprints. And ultimately, what you see here is a snapshot of the Slices Academy website, where a lot of the content is stored that can be reused for tutorials or classrooms. So as I said before, the experiment is at the middle. So basically, when you want to develop an experiment on top of the post-5G blueprint inside of Slices, you have to be thinking that this is an experiment. So you first define the experiment, and this is a snapshot of the current or the version 2 of the blueprint, where you're actually defining the parameters of both the core network and the radio access network that's running in a particular site or in a couple of sites. So it's a web-based interface for defining the networking components themselves. Afterwards, you reserve your resources. So you can see here there are a collection of machines in various sites. And you have a notion of a calendar where you reserve the resources for 2 hours or 4 hours, or in the future, even longer than that. So you book your resources. Then you run the experiment, which takes a certain amount of time, and you collect the data. And the data collection is important too, because it is a metadata, and it adheres to the open principles of EOSC. So if I just go to some lessons that are learned, basically today the blueprint can be deployed on premises in some of the sites. It can be deployed also on a public cloud, for instance, Google Cloud Platform. There are various test beds that have done it for training purposes, and even integrated other types of technologies like the Amarisoft RAN, which was done with my colleague Philippe Martins, who will talk after me, at Télécom Paris. So there's a lot of diversity in the types of equipment. Many experiments, this number is not completely up to date, have been made by the public so far. There is network interconnects between the various sites, some of them using commercial internet, some using dedicated links, and also VPN services between sites. There is today a tested identification and authentication mechanism where users make use of the light federation from Slices, and now there's actually a push to unify different certification systems, so that we can add more testing sites, and basically people test first in virtual environments and then in the real environments. I'll skip the equipment. This is an example of one site, the one that is driven by Eurocom and INRIA in Sophia Antipolis. You can see that it is distributed between the two sites. There are 2 data centers, one at Eurocom and one at INRIA. The INRIA site has an anechoic chamber, and the Eurocom site has deployed equipment indoors and outdoors with both infrastructure equipment and user terminal equipment in various places. I think what you will see in the future is that there will be new features, basically finer control of the infrastructure in terms of the slices and subscribers. There'll be multiple implementations. Today it's primarily open interface, but there will be other software packages that are added. There will be more operability tests and to construct compatibility matrices between the different software packages. And I think you'll also see more use of natural language input models, for instance, using large language models to help the users actually deploy network resources. Today there is one entry point, and it's doc.slicesri.eu, and you can go and you can actually, if you're a public or even a nonprofit research organization, you could actually use the infrastructure free of charge. What I described here was the post 5G blueprint. There are other blueprints that are being developed in other contexts. For instance, the Cloud Edge Continuum, and also a federated learning blueprint, and many more basic services than what I've described here are also available. If you have any technical or operational questions, you can contact any of the people here on this slide, and I'd be happy to take any questions now.
Well, we do not see any hands raised so far, nor any question in the chat. Okay, so let's keep going. And with that, first of all, thank you, Raymond, for enlightening us on these facilities. And with that, now I would like to invite Philip Martin, who is also the research director at IMT, and he's going to present us on the specific test beds for embedded AI and edge computing with slices. So, Philip, the stage is yours.
Thank you very much, Pooja. Let me try to share my screen.
We can see your slides in the presentation mode. Thank you. Go ahead.
Okay, thank you. So let me start. Hello, everybody. So as Pooja said, my name is Philippe Martins. I am professor at IMT in Telecom Paris. We have several sites in France. And this is a joint presentation with my colleague Cedric Adji from INRIA, Palaiseau. So today I will introduce you the test bed we have started to design and to develop in the context of the PEPR project, national project presented before by Philippe Peignet and Raymond Knopp. So the presentation here will concentrate the attention on use cases that combine artificial intelligence, embedded artificial intelligence with IoT communication. That's the purpose of that test bed. So let me, I don't know if you can see the next slide. Yeah, it's okay. So what's the next generation solar IoT platform? So as I said in the introduction, this platform is a part of the French national project, PEPR Réseau du Futur. And in fact, it makes part of the work package designed for the work packages, which design is for the test beds. So this platform is dedicated to provide the researchers facilities to do experiments for research combining the use cases of cellular IoT and the use of embedded AI at the edge. So usually when we have to do that, we have some difficulties to face. The first one is to provide an end-to-end facility that will allow the researcher to do its experiments. So as Raymond said before, we have many things when try to do that. We need to provide a development platform. We need to provide tools to retrieve data and measurements. And we need also, in some situations, to provide tools that allows the protocol analysis if you are looking at protocol level. So this platform, to summarize, will emphasize on communication of next generation cellular networks for IoT. And it will also use also specific embedded AI capabilities such as tiny machine learning and edge AI. And all that stuff will be used in hardware provided at UE level and at edge level. So that's basically the outline of the platform. Next slide. So it's going too fast. Yeah. Oh. Okay, so if you have a look, sorry, okay, yeah. If you have a look at the history of the project, in fact, that test bed comes is a result of a long history, because in the past, 10 years ago, we have developed a national infrastructure devoted to the IoT research in ISM bands, okay, not now. So this is why we have started to extend that facilities to cellular use cases. And the final goal, in fact, is to integrate that platform in the slices for context presented just before by Raymond. So today, the testbed relies on two sites. The first one is hosted at INRIA. This is where, in fact, you will find AI embedded facilities. And we have another site which is hosted at Telecom Paris, where we have a Faraday cage, where many experiments are conducted in a protected environment. And the combination of the two sites allows us to provide the NGC IoT platform. So let's have a look, in fact, at the story of FIT IoT Lab. So FIT IoT Lab, its main purpose was to provide an embedded system research framework to do experiments at sensor level. So this project, in fact, has a long history, and it provides support for many kinds of hardware, as we can see here. And it provides also support for many protocol stacks. So all that protocol stacks, they operate in ISM bands, so they are not cellular ones. So, and we have also a basis that provides the support of many embedded operating systems that are supported currently in the platform, and that allow researchers to develop their own protocol stacks on top on different kinds of hardware. So that's in fact the income for NGC IoT. So now, if you have a look at what we are doing today, what we are doing today is the integration of AI hardware, embedded AI hardware. So currently this is Jetson hardware that we deploy in the Faraday cage in a protected environment, but also that we intend to deploy in outdoor environment, because in our site we have 5 or 6 antennas deployed in B38 band to allow to do experiments in the outdoor environment, so to show that one specific experiment is scalable. So currently, so we are under the deployment of this hardware, and we have also a first release of a reservation system, because what we intend to do here is to make it possible for the researchers to make reservations of that facilities. And when in fact the test bed will be fully operational, that NGC IoT will be integrated in the Slices FR project. So currently, if you have a closer look at the development stages, so we have currently 10, I don't give the number here, but we have deployed already 10 embedded hardware Jetsons plus LTE modules in band 38 so which is approximately in our case between 2,605 megahertz and 2,615 megahertz. So that module is already deployed, so they can already be used from some experiments. And the technologies that are provided today in cellular IoT is LTE-M and narrowband IoT. We plan to provide 5G RedCap UEs for experiments. We currently already have the infrastructure, but we are still looking for modules to allow experiments for 5G. And as I said before, as we are starting the deployment, in fact, in outdoor, this is something which is still under test to show that what we intend to do is scalable. So if you have a closer look at what is inside the platform and GC IoT, so in the AI IoT part, what we can see in the figure at the top of the window, this is the reservation system. So the user, in fact, through a web portal, he has an account, so he can make a reservation for a testbed to do AI computation. And then, in fact, for example, here, green means that the system is fully operational and is free, and yellow will mean that the system is operational and is already currently used by one given user. So what we have here, we have one external user that connects through a VPN to the platform. Each user will be handled by a virtual machine, and inside, in fact, the test bed, we have one VLAN per user, and so you can connect directly to each JSON that the user wants to use in the context of his experiment. So here we can see pictures of the platforms that are currently used and tested for the test bed. So now, if you want to combine the use of embedded IoT with a cellular, so this is something, in fact, that is also currently under test. So in Riyadh site, but also in Paris site. So what we can see here, it's a system that combines edge AI plus cellular modules. Here we have modules provided by a French manufacturer. So we can support 4G and narrowband IoT LTE-M. 5G it will be for a near future. So currently this is the two that we have. And we can see that we have two AI embedded modules. Sorry. Oops. We did that because we intend to allow the deployment of split computing facilities. I will give you more details about that just after. So here we have two JSON modules, and everything is powered through power over internet. So just a picture, in fact, showing you what is currently available today. So here we have an image of the reservation platform. And here we have the two resources that can be selected by the researcher to do experiments. That one in the RIA room, and the other one is in Telecom Paris room. One other important thing is to have access to logs generated by your experiment. So this is something also we provide, which is still under construction. And the idea here is, as we provide an infrastructure to do UE, to do experiments at UE level, we need also to have facilities to protocol analysis. So this is something that you provide at the base station level, and the researcher will have access to that. And as we can see here, we can have access to all the protocol details from the physical layer signaling to the application level. And we have also some dedicated screens that will provide you information on the air interface activity, the physical channels used, where the resources have been used for a given user. So that's something that can be useful for researchers when they deploy the experiments and then they want to have a close look at what is going on in their experiment. Let's go back to what I said before regarding the use of two embedded AI models. So that's one, just to give you an example of what can be done. So here we use the platform to do what we call split computing. What does it mean? Assume that you have a system with a sensor, for example, one camera, and that camera is coupled with an LTM system to transmit images. And what you want to do is you want to do pattern recognition locally, and you want to do, in fact, that in real time because your system at UI level is constrained. So what you will do is you will take your neural network, you split it in the two different parts, and one part, well, the first part located at the edge will do one part of the processing. And if, in fact, the local UE determines that the processing requires additional processing, in fact, you will send the SMET form of data, SMET data to the edge or to the cloud to perform complementary computations and to determine, in fact, if in that case you recognize one image, if it's the recognition is successful or not. So that's something, in fact, that has been published, just to give you one example of use case of experiment where the HGC IoT platform can be used. That's all, in fact, for my presentation. So if you have any questions. Hello?
Thank you, Philip, for the presentation. So the floor is open for questions. So we have a question which is in the chat. Maybe would you like to open your mic and ask the questions directly, or? So the question is, which OS are you using on the Jetson Nanos?
Yeah. Currently, in fact, what we are the hardware we have is quite old. So I think if I remember well, you are using Ubuntu 18.04.
Thank you.
But if you want, I can provide more details regarding the hardware and the operating system that we're using.
Yeah, it would be helpful if all the presenters could also drop their email IDs in the chat with their topics maybe, so that if someone is interested, then they can also write to them directly. So in your presentation, Philip, you also mentioned that currently the resources that you have are in the frequency band of 2605 to 2615. Do you also megahertz? Do you also plan to have more bands being available? And this is for both uplink as well as downlink.
What we have today, in fact, it's the same in. If I give Raymond will answer, it's the same in Eurocom. The difficulty we have, in fact, is to have outdoor frequency bands because we need for that an authorization from our national regulator. So the answer I will give now is only for the site I am located, because perhaps the answer will be different for the other sites. So from my side, in Palaiseau and Saclay, currently we have only the authorization for one band, which is the band 58. We plan to have access to other bands. In fact, we have requested the N, if I remember well, is the N 77U. That's something, in fact, we are requesting for indoor and for outdoor, but we don't have the authorization yet. The only band we have to perform outdoor experiments is the B38 from our side. But Raymond, perhaps you can say more regarding Sophia.
In Sophia Antipolis, we're operating at 3.9 gigahertz. It's a 100 megahertz channel at 3.9. So that's this N77U. We also have a 40 megahertz channel in N78 at 3.4 gigahertz. It has to be renewed every 6 months, so it's a little bit complicated. But the other bands also that Philippe is using, those are more flexible in the sense that the regulator gives us longer periods to operate in them. And 77 also, but it depends on the region that you're living in.
Okay, good. Thank you.
Otherwise, in fact, if you want to use other bands, we have to do the experiments in a protected environment, for example, inside the Faraday cage. But of course, this is not something. It's convenient for the first stages of experiments. But if you want to test scalability of one proposal, you need to perform outdoor experiments.
Thank you.
I think in the near future, we will also have outdoor millimeter wave, so 20, 27, 28 gigahertz. Currently, we're only operating that indoors.
Yeah, I mean, with regards to how the technology is evolving towards 6G, we are all going to millimeter wave. So I think that is the most used or potentially proposed band that the experiments will gradually start to take on.
Well, I think also based on the availability of the necessary RF equipment, it's not unlikely that in the coming year we will operate also between 6 and 8 gigahertz.
Yep. Thank you. I have one question for Philip Besner about the anechoic chamber with the antenna measurements. Philip?
Yeah.
Okay. So you showed the facility about the anechoic chamber for far field propagation. So what is a typical range that you see and the type of experiments that could be engaged with that?
Well, the number of experiments is huge, I think. Anyway, if you look at the different kind of antenna systems we could foresee for the future, many of them will deal with beamforming. That is to say, in that case, instead of having one antenna, you have a set of antennas which are fitted with different types of signals, which vary in amplitude and phase. And in that case, one of the problems we have to face is to manage the number of measurements available in a certain period of time. So to do it, of course, once again, it will depend on the frequency range. You mentioned about the fact that, of course, the bandwidth in the 6-7 gigahertz range, or the bandwidth in the millimeter wave range in between 24 and 28 gigahertz, which these involve different sets of anechoic chambers, different measurement distances, and especially in that case, we will have to face with different configurations of these feeding signals for antennas. So in that case, it's about using in a clever way these kind of test facilities and to adapt them in order to provide a sufficient set of measurements in chosen configurations. So this is one of the maybe challenges for the future, is how to prove that with a limited set of measurements, we are able to get RF systems or RF antenna systems which comply to the specifications given by any companies. So this is one thing. Another maybe possibility is to use alternative measurements rather than anechoic chambers environments we could use also reverberation chambers, not exactly for the same targets, but again, it is possible to check for the total radiated power for the measurements of multiple antennas, which are fed with different signals once again. So instead of measuring the antenna pattern, this time we control that the total radiated power is the same, whatever the configuration of the feeding signals of the antennas. So this is something which is complementary to measurement of radiation patterns. And it could be done, of course, we need different, we need to move from one environment to another, but this is something which is a degree of freedom which is quite interesting. Another part of illustration that I could make here is about the RITS, reconfigurable intelligent surfaces. This is something which is dealt with in many research programs nowadays, and is also foreseen for the 6G communication because it could solve many difficult situations where the propagation is fading somewhere. So there is a something which is can be made with these reconfigurable surfaces in order to enhance the signal to noise ratio in different circumstances. That to do that, I think this is, I take this example because it's a very nice example about the transversality of our platforms, which have been presented by the three of us. I mean, risk first has to be characterized in a way of proving that it is able to manipulate the wavefront and in a way to avoid, let's say, or to minimize the losses, because you cannot take a risk without making losses in the materials which consist of the risk itself. So to characterize these losses, you do not need any in situ experiments. You need a lab experiment. But what is nice to see here is through the set of platforms, we can have first a test of risk for their performance itself, and then we can use the risk in use case scenarios in such platforms as presented by Raymond, for example. So, you know, there are also anechoic chambers which are equipped with radio access, and they could be manipulated in some way so that we can arrange the set of radio access spatially, and then in between walls or in between or parts of different walls, or we can reconstitute walls or whatsoever. And then we could put then the risk itself in this type of environment. And then we have to control the risk with the base station to control the different elements of a risk. So this is something which is very interesting to manipulate, and also it serves, in my opinion, also the community that try to design risks or appropriate risks for the usage.
Thank you. Thank you very much, Philip. So with that, once again, I would like to ask the audiences if there is any further question that you would like to ask. So just to let everyone know that already the session was being recorded, and the recording will be available on the event page post-event in some time. And the contacts of all the presenters are there in the chat, so feel free to reach them. And if there are no further questions, then I think we can wrap up. So I would like to thank all the presenters to kind of give us an overview on the experimental platforms that are available in France. And I think this should be really helpful for all the researchers, SMEs, industry players to kind of co-develop and experiment and validate their experiments on the cutting edge technologies. And this would further help in shaping the overall technological landscape that we have here. So with that, okay, I see one hand.
Yes, hello. I have a question for Raymond. I wanted to ask that for this millimeter wave for N258 band, which kind of UEs you are using for the testing? Any commercial or some testing UEs for that?
No, it's all commercial. I mean, it depends on the application. Sometimes they are Quectel 530F modules, which are really designed for a CPE type application. But we're also now using some US smartphones. But those also
Okay.
require a frequency range 1 carrier because they do the what's known as NRDC, so dual connectivity NR. So you have to have an FR1, if you like, network deployed, and it will always remain connected on FR1. And when you're in coverage of FR2, it will open a second carrier on FR2. But that's the phone. The modules are always running in full standalone mode of FR2.
Okay, thanks.
Anyone else has any question? Looks like not. So thank you all for participating and enlightening us to all the presenters about the innovations and the experimental setups that you have in France. And I hope all these experimental initiatives would help to shape the technological landscape. And we see you in the next webinar soon. So with that, have a great afternoon and have a nice kickoff to the week. Take care, everyone. Bye-bye.
Thank you very much. Bye-bye.
Bye-bye. Thank you.